Welcome to the University of Texas at Austin, to the Real-Time Digital Signal Processing Lab class. I'm Professor Brian Evans. This is Lecture 2, Part 2, and the topic here is Introduction to Digital Signal Processors. And on the title slide, I would have covered this in Part 1, but just to cover it, these are three architectures for digital signal processors over the years. And the very early ones, which go back to 1982, used an accumulator architecture, and this had some disadvantages. One is that I had, in order to bring any data from local on-chip memory into a CPU to work on that data, I had to bring it from memory, which is kind of shown here, and I always had to bring it through an accumulator. So an accumulator just performs addition, but it does so at extended precision so that we don't lose the extra bit that's generated when I add, in the worst case, two numbers together. So I have to go through the accumulator before I file. And I had no choice. I could not directly load. And the reason for this is that this is a common way we'd implement multiply add operations. We'd always go through an accumulator. So this was an older view of what a digital signal processor would do, which is lots of additions. Also, and lots of multiplication. So the multiplication would feed in to the upper part of the accumulator, and we could bring in the lower part to add to that result. Okay, so that's early 1980s. A little later, I suppose this would be late 80s and early 90s, at least you got the option to bypass the accumulator, and you could load directly from, again, memory to register file. Again, same graphical representations here. And the memory on chip on these processors the memory cells were very fast. They could be read at the rate of the instruction cycle always. Okay, so that's the more recent architectures. This starts around 1996. So this is late 90s. We're finally to what is more commonly done today, and that is a load store architecture. And in the load store architecture, we break operations to their simplest components. And so now I'm no longer going through the accumulator from memory, because I may not always need to do an accumulation operation. In fact, I'm not always doing one. So now it's the more common case where I have on-chip memory, and I can load a register directly from on-chip memory, and I could also store from a register to on-chip memory. And if I need to do math with it, fine. Now I can separately do multiply and addition in the CPU core. And so now I've decoupled the memory subsystem from the CPU core that does all the actual instruction processing. And this is nice, so I can decouple the design. Also with load store architecture, the next step would be to decouple multiply and addition. They don't always go together. And so and that's what we'll talk about today with the C6000. So this would be the processor we're using in the lab component. This is the C6000 digital signal processor from Texas Instruments. So this, again, fully decouples I/O and specific operations, and no longer assumes that every time I want to do a multiply, I'm going to do an add as a result. All right, so let's move ahead to the C6000 slides, which starts on slide 8. So this is a simplified block diagram for the C6000 family. This is abstract. It is not in any way indicative of how many transistors are needed. This is a very high-level block diagram. So the goal with digital signal processors in general is to get power consumption down and at the same time provide enough computational performance and input-output capabilities to keep up with streaming input signals and to produce streaming output signals at a particular rate. All right, so earlier in the class, back in, I think, Lecture 0 slides, we talked about what real time means. And so real time, and I quoted Professor Yale Pat on our faculty. So real-time, in our case, means guaranteed delivery of data by a certain time. And this guarantee is 100%. We won't make it 90% of the time. We're going to go for 100% delivery. So on any digital signal processor, you're going to see support for this. And for streaming I/O, we're going to see that this particular block plays a critical role. This is direct memory access. And for direct memory access, we are going to take in a buffer of samples. And when that buffer has been read into local on-chip memory, we trigger an interrupt for the CPU core to then process the data. Likewise, we can have DMA off-chip, which also does block transfer, buffer, or frame-based transfer of a block of samples to an external chip. Again, one of the reasons this is so useful is that instead of doing one sample at a time and trigger an interrupt, we want to do a block of samples and then trigger the interrupt. This allows us to only have the overhead to service an interrupt every block of, say, 100 samples or 20 samples, instead of having to service that overhead every sample in triggering an interrupt to let the CPU core know it's ready. The third way we can get data on and off the chip is through polling. The problem with polling is that we're constantly using the CPU to poll a peripheral control register to see if the data ready flag or the data ready bit is set. So this uses up a lot of CPU resources. The direct memory access has two real big advantages. One is this does not use any CPU resources at all in getting the data on and off the chip. And second of all, it can do block transfers. So I have some flexibility in what that block size is based on the capability of the DMA controller. There's actually a third advantage with the DMA controller in that the DMA controller can perform some basic logic operations as data comes into the chip. I can do things like zero pad data, sample by sample. I can do matrix transpose, that's to say reorder data, permute data. So the DMA actually has some functionality built into the DMA controller that does not in any way burden the CPU. It is a separate controller with a separate functional logic and separate functions, really, to complement what the CPU core can do. So DMA is really good at handling streams of sequential data and doing bitwise operations on the sequential data as it comes into the on-chip for the processor. Now, there are a number of other peripheral controllers that are useful and oh, by the way, there can be more than one DMA channel. There can be more than one DMA input channel. There can be more than one DMA output channel. It just depends on the chip that you have. Some other configurations, some other external interfaces to the PC. So I can download code to the board or to the chip directly. So there's some other timers, kind of cool to check how long things are happening or controlling things externally with digital lines. Those are all very useful. But the primary peripheral controller for the lab that we're going to use is the DMA controller. This is the one that really helps us meet a real-time delivery of data because it allows us to stream data at a high rate without burdening the CPU core. Okay, so now let's look at the CPU core for a second. The CPU core has, for the C6000, the DMA control is something that's fundamental in a digital signal processor. They've been there since the 80s. This is useful. It's not just on the C6000. And the same thing with the host port and timers. These have been around a long time. And DMA controllers are useful in other contexts besides processors. Instrumentation has DMA control to get buffered I/O off of a spectrum analyzer onto a processor or a board, for example. Okay, let's go look at the CPU core. The CPU core is what's shown here. The CPU core, and there are some more slides on this to follow, but the CPU core has got a lot of functionality exposed. It's just not one processing block or arithmetic logic unit. Instead, I now have 8 blocks, and they can run in parallel. So the first 2 blocks up are D1 and D2. These are data blocks. These control the loading and storing of data from local on-chip memory to a register and vice versa. So these are data reads and writes to local on-chip memory, and it's going to go over one of the two internal data buses. So one of the fundamental ideas in digital signal processors is called the Harvard architecture after Harvard University. The Harvard architecture says that because the application space does so many calculations on streaming data, what we'd like to be able to do is separate the data buses from the program bus, and that's what we do. So in this particular processor, we have two data buses, and we have one program bus. So internal to the chip, so internally there are two data buses. And anyone recall, do you recall how wide each bus is? Or the word size for the processor? Do you remember what the word size is? Word size. What's an integer for the processor? How many bits? 32, good. So two data buses, and each is 32 bits wide. Okay, so I have two internal data buses and one internal program bus. Okay, the internal program bus is pretty wide, as we'll talk about in just a second. So D1, data unit 1, works with data bus number 1, and data unit 2 works with data bus number 2. And they can run in parallel, so it allows you to do two reads or two writes on each cycle in terms of throughput, and we'll talk about that distinction soon. All right, so I have 6 functional units, or computational units. I have 2 multiplier units, M1 and M2. I have 2 logic units, L1 and L2. I have 2 shifting units, which also do logic operations, S1 and S2. So it turns out for L1, L2, S1, and S2, I can do an add operation. I also can do an add operation in the data units, although that's normally used for pointer arithmetic, not so much of just doing additive calculations. For example, in just summing up numbers to get a final result. Okay. Now, the processor core is actually split in 2 pieces, and they're somewhat separate. And so the 4 functional units that have number 1 with them, the data unit, multiplier, logic, and shifter unit, read the values from register file A. And register file A, in the default C6000 architecture, has 16 registers, and each register is 32 bits, one, which is the word size for the machine, for the processor. And likewise, the 4 other functional units, data unit 2, multiplier 2, logic number 2, and shifting unit number 2, read by default and write to the register file B, which has 16 registers by default. Now, on the C64000 subfamily, we actually have 32 registers in each file instead of 16. So we have more registers. But the default architecture is 16 registers in the A file and 16 registers in the B file. And they're numbered A0 through A15 and B0 through B15, respectively. All right, that's somewhat familiar ground. Now, one of the problems, if I want to get data from an A register to the right set of functional units, I incur a penalty. And that penalty is that I'm fully connected from the register file A to the 4 functional units that are marked number 1. But in order to get across this divide to the right-hand side, I have to go through an extra delay. And basically, it's a crossbar switch, but I have to go through it. It takes 1 cycle of delay for the values in register A to get over to the right-hand side to one of these functional units marked number 2. And vice versa, if I want to read one of the B registers on the left-hand side, the functional units denoted as number 1, I also incur a 1-cycle penalty. Otherwise, there's no delay in getting the values directly from the registers. The same delay occurs when I want to write. So if let's say I add two numbers together in the logic number 2 unit, and I want to store the result in let's say A11, then I'm going to incur a 1 cycle penalty before the data is ready in A11. So what this means from a programming point of view and from a compiler point of view, I want to be able to separate the calculations and the data and where that data resides in registers into 2 pieces and try to keep those 2 pieces as separate as possible. Now in practice I can't always do this. I have some crossover delay that it's just going to happen. Okay, so at the bottom again of this of these functional units are control registers, and can you name me some control registers, flags that you've seen in the past? I'll give you one to start with. How about it's 0 or not 0? That's a flag. It was the last operation was 0 or not 0. You think of any other flags?
Negative, positive.
Yeah, negative, positive, overflow. Overflow is a control bit, absolutely. Okay, so the bad news here is that on the C6000, what happens, there is almost no control. This control register is very simple, and it only flags, I think, overflow, if I remember right. And it doesn't have 0, not 0, or any of that. Okay. And the overflow is, yeah, there just isn't much to go with in terms of control registers. So what this means is in practice, if we want to generate, was a value positive or not, was it 0 or not 0, we're going to have to find some other way to test that. We're going to have to generate the condition explicitly on our own. Okay, now for a memory map or the memory subsystem, what's shown here is the basic view, which is I have program random access memory separate from the data random access memory, and the program RAM can include a instruction cache. And so we can talk now about the program RAM and the program bus. So if you look at this, each of these functional units, and there are 8 of them in total, is a 32-bit processor itself. And since all 8 can be executed or be executing in parallel, the actual instruction word is 32 bits for this one, but each one is 32 bits wide. So if I concatenate 8 32-bit instructions, I end up with 256 bits. That's pretty long. And so this is so the program bus internally, this is internal to the chip. I have one program bus, and it is 256 bits wide. And again, that's just the extreme case that all 8 units can operate in parallel. Not always the case. It depends on how you write the code in assembly language or how the compiler generates the code in assembly language. But the extreme case is I could really have a 32-bit instruction for each of these 8 units, and so in total it would be 256 bits wide. So the program memory is allocated in terms of 32-bit entries, and worst case is I would collect 8 of them to dispatch at the same time for execution to the 8 data units. Now data is a little more complicated. It's shown here as a block, but the reality is it's actually multiple banks of memory, and they're going to be tied to data bus 1 and data bus 2. So typically the memory, it depends on the chip configuration, but often this memory is what's called dual ported, which means I can do 2 reads at one time per cycle, and one can go out to data bus 1, one out to go to data bus 2. But to reduce cost, the memory may not be dual ported, it might be single ported, which means I can't read twice in the same bank and put one value out on data bus 1 and another value from the same bank of memory to data bus number 2. So what we try to do in practice to keep costs down, it'd be great if this were single ported. Now that means that I'd be very careful where I put constants and data, because I don't want to access the same bank of memory at the same instruction cycle, or in the same instruction cycle. And we'll talk more about that as we go in class, because this will affect how we do a filter implementation. It's also possible to have data cache. It's configurable, so you may have it or not. Just depends on the memory map and configuration and so forth. Often we don't need one, but sometimes we'll use one. We don't need one for the low-level calculations for filters and sinusoidal generation, but it's possible that you may need one configured for other things you're doing. Questions on simple? We got some slides to go. That's all the on-chip stuff. Off-chip, the bus that's off-chip is 32 bits. And there's only one of them. And this is also true if I want to go off-chip and fetch code to update my program RAM, I can only read 32 bits at a time. And when I go off-chip, I pay a pretty severe penalty. It can be up to 15 cycles of delay to get the value back. So going off-chip has a high penalty, and it's one we'd like to avoid. And we can avoid that in two ways. One is we can bring the data we need that's streaming at us through the DMA controller and the DMA channel. Second, if we do it right, we want to fit all the program code on chip and never have to go off chip for more code. So now it becomes important to keep our programs small in terms of assembly language instructions to fit on chip if we can. If we need to go off chip, which can happen for data that we might have to store off chip simply because we ran out of memory, we have to make sure that when we program this, we can basically prefetch this data early enough so that the 15 cycle penalty doesn't prevent us from guaranteeing delivery of data. So we have to prefetch early enough so that when the 15 cycles are over, that is before the time we really need that data to be available in local on-chip memory. So the flow from off-chip memory goes to on-chip memory, and then anything that's in on-chip memory can be brought into a register, and from a register we can go back to on-chip memory. But again, for streaming data, we want to use a DMA channel, and for the code, we'd like to fit everything on chip if we can to avoid this overhead of going off chip. Going off chip is fine for asynchronous things where we don't have a timing constraint or deadline. We, download things into the chip, that's fine. Maybe at configuration time, but not while we're handling streaming data. We like to avoid going off chip if we can. All right. So this is in slides now, some of what I've said already in words. So this processor has a very long instruction word of 256 bits because we have 8 32-bit functional units. Each functional unit has one cycle of throughput, which means that for this base architecture, which does not have floating point in it, this is true. Now, when we start adding floating point, we'll see that some instructions take longer than that. But for the base architecture, each functional unit has one cycle of throughput, which means that so if I issue 6 multiplies in a row, for example, integer multiplies, I'll just do, let's say 5, just to make it easier on me. So I initiate 5 multiply instructions, and in this base architecture, this is 16 by 16 bits to give us 32 bits. That's the base integer multiplication. What it means is a multiply for this particular instruction, I have one cycle delay. This is only for multiply. For multiply, I have one cycle of delay, and I have one cycle of throughput. So it means that after one cycle of delay from the first multiply, the next cycle I'll get the result. But while I'm doing the next cycle, this multiply has already started. Right, so if I look at so basically if I look at it, these are instructions, these are cycles, these are sequentially executed. So I have cycle 0, 1, 2, 3, and 4. The first data value is ready here. So data is ready here. This is data from number 0 is ready actually here. So 1, 2, 1 delay. Okay. Data is ready here. Okay, so data 0 is ready. Here, this is from data from the multiply from 0 is ready. Here, the data from number 1 is ready. Here, the data from number 2 is ready. And so forth. Okay, so this multiply, and it kind of makes sense when I multiply two numbers together, I have to do some multiplication, I have to worry about some carries. The multiplication is a bunch of addition operations. So it takes a bit of work to do this just right. So it's more complicated than addition by itself. So I multiply, one cycle of delay, and then I start getting the results one at a time. And by the sixth execution cycle, my multiplies are now all finished. So I have 5 multiplies operating. Cycle 1 I issue this multiply. Cycle 2 I issue this multiply. Sorry, cycle 0 this multiply. Cycle 1 this multiply. Cycle 2 and so forth. And on cycle 2, the multiply from cycle 1 is finished. In fact, it's ready at the beginning of cycle 2, at the end of cycle 1. And then these data values go boom, 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 and they're done. So at the beginning of cycle 6, the last multiply has finished its calculations. So it's ready at the start of, so really data 1 is ready at the start here, to start here. So this throughput idea is pretty important. It means that, so if I issue 5 multiplies in a row, sequentially, the results of all 5 will be ready in 6 cycles. So 1 cycle longer, and that's this due to this 1 cycle of delay. Okay. But the throughput is, after I incur this 1 cycle of delay, my throughput is 1 multiply per cycle. It's going to come out of the multiply functional unit that I'm using, whether it's M1 or M2. Okay, so go on. So basically it's 1 instruction cycle per clock cycle, which is typical, and each functional unit runs at the clock cycle rate. So I can do 8 instructions in 1 cycle because I have 8 functional units. Data word size and register size are each 32 bits wide. Again, 16 registers in each of 2 data paths. And on the C6400 family, which we're using in lab, we have twice as many registers. Now there's an interesting story on this processor. There's a 40-bit mode. And the way you store that is you store 32 bits in 1 register, and the next register would store the remaining 8. So I can use A0 and A1 to store 40 bits, or A2 and A3. And so this kind of brings up something interesting in the C language. So in the C language, which we want to map this to, if we map the C language to this architecture, is that on this architecture, the size of the int data type is 4 bytes in the C language. Okay? And the size of short is, what do you think? What's the size of short? 2. And char? 1. And long?
8.
You would think 8. There's a hint.
4.
Yeah. 5. Okay. So there's so the long int maps to this 40-bit long word, if you will. That's why long word's probably too strong. But this 40-bit value, and this shows up in some speech compression standards, and there's some other reasons to use it, which we'll get to later. It allows you to add to extended precision, for example. I can add 32-bit numbers, which in the worst case gives me a carry, and that means 33 bits. So I could use this 40-bit mode to add 32-bit numbers and still keep full precision of the results for quite a while until I hit 40 bits of accuracy. All right, so there are two parallel data paths. I've got 2 data units, 2 multiplier units, 2 logic units, and 2 shifter units. Now the shifter unit, again, this is all for the base architecture. There's no floating point data types or arithmetic in this base C6000. That requires an extension to the base architecture, which exists, and there are a couple of different extensions for this. But this is all, the base architecture just works with integer values, or you call it fixed point values. So it's going to be 32-bit. The multiply is 16-bit by 16-bit, giving a 32-bit result, integer. I can add two 32-bit numbers, and I can either store that as a 32-bit result, or I can store it as a 40-bit result. And we'll talk about, okay, in the data unit, what's interesting, and this is very common on a digital signal processor, there's the usual addressing modes of indirect and basically indexing into an array, the usual things. But in addition, there's a modulo operation, and any idea why that's useful in processing signals? Is there a data structure that uses modulo indexing?
I know we used it in the base
So you could do, this is just counting, or was this?
It's just so it would be within one, like from 0 to pi, and then bring it back to 0.
Okay, that's a modulo for calculation of just an arithmetic calculation. But this is modulo as an addressing mode, which is I'm trying to address into an array, but I want to do it in a way that if I go outside the bounds, I wrap back around. I'm always in bounds in my array calculations. Okay, so this shows up in circular buffering, which we'll need quite a bit in lab. This is how we manage the delay line on a finite impulse response filter. This is how we maintain record of the previous input values into an FIR filter by means of a circular buffer. Okay. There are lots of subfamilies within the C6000 base architecture. The first one was the C2000. These are, at this point, obsolete. These were first fabricated in 1999. They're around for legacy reasons, but they're not being actively developed, or new components are not being developed in this family. The other 3 families have active development, and for different reasons. So the one you're using in lab is, interestingly, the 6748. Now, it takes features from both the C4000, 64,000, and the C6000. These feed into your part. Okay? Interestingly enough. So the 67 means it's got floating point extensions, and this 4, although I can't have 2 different digits in that location, this sort of implies some connection with the C64000 family. C64000 family, if you remember, has double the registers. That's important because registers are going to contain the values we compute with, and on the C6000, the registers are quad ported, which means I can do 4 reads of the register in one cycle. So on the C6000, the registers can be read 4 times in the same cycle. This is quad porting. But no more than 4. But that's unusual to have to read the same register more than 4 times. I haven't encountered that this is a real limitation. Okay, so your processor combines the floating point extensions of the C6700, which I'll talk about in a few slides, and the extra registers from the 6400 family. And in addition, it's in the OMAP, which is Open Multimedia Architectures Platform, and it has an ARM core in addition to your DSP core. But the DSP core that you have is the 6748, again, which takes its properties from these two subfamilies. The C6600 family is using basically cellular base stations, and it runs pretty fast. So the high end has got 8 cores running at 1.25 gigahertz, so you have 10 gigahertz of clock speed and 8 instructions per cycle. So it's pretty capable, right? So that's 80 billion operations per second. And if you use floating point, single precision, you get a throughput of, believe it or not, the throughput here is still 80 billion floating point calculations per second. It's pretty serious. All right, so the C6700 family is meant for, it's in a lot of audio products today, but it's also available in other components or other types of application spaces. So your board has the following. So if you ever get questions from a prospective employer about what you did in this class and they ask you about the lab component, you should be ready with this. This is a 2-star, pretty important stuff. But you also need this for lab reports and so forth. So you have a CPU that runs it internally. So your CPU runs at 375 megahertz. Doesn't sound like much. But remember, you've got 8 operations per instruction, or per clock cycle. So that amounts to 3 billion, or 3 GIPs, if you will, 3 billion basic operations. You can do, since you have 2 multiply units, you can do 750 million multiply accumulates per second. And that's also true for not only 16-bit by 16-bit multiplication, but also that's the throughput for 32-bit float times 32-bit float. Pretty fast. That's enough for what we're going to need. Now, the downside, not a lot of on-chip memory. Remember, a word is 32 bits. So not a lot of on-chip memory. It's not megabytes, it's kilobytes. So I have 32 kilobytes. So so a word is 32 bits or 4 bytes. So I have 32 kilobytes of program memory on chip, 32 kilobytes of data memory on chip, and 256 kilobytes of level 2 cache, data cache. So be pretty careful how I program this, so I can fit all the code onto chip without having to go off chip. Now the good news is lots of stuff on the board, lots of memory on the board, in both random access memories, read-write memory, and also read-only memory. Lots of stuff off the chip on the board. All right, so let's talk about the base. This is a C6000 base instruction set. It's for all those subfamilies. They just extend this in one way or another. So I've got, if I look at it in terms of functional unit, and I don't list everything, I'm just giving you some of the more common instructions. There are variations not shown here, but what do we need to do? Things like add 2 numbers together. Let's see, I need to branch. It's always good. Kind of hard to write a program without a branch statement. This is to create a constant. So that's better than loading a constant in from memory, because if I load a constant in from memory, I have to wait. There's some overhead when I load. I guess I haven't talked about that yet. So load and store has 4 cycles of delay. For load and store, but 1 cycle of throughput. So if I want to initiate a load, this is from on-chip memory, I have to wait 5 cycles for the result to be ready. So instead of loading a constant in from on-chip memory, it's a whole lot easier just to generate it, because I can generate it from the CPU core in 1 cycle, not 5. So This is move constant. I can zero out a register. Pretty important to set up an accumulation register. What else can I do here? I can do the say our logic operations and or exclusive or and so forth. I can move between registers. I can move the control register into one of the general purpose registers. I don't do that very often, honestly. I have some variations on addition and subtraction. So I have saturating add and saturating subtraction, which means if I hit if my add generates an overflow, I've gotten too large for the intermediate result, or the result's too large to fit into 32 bits. Saturating add says the result will be the maximum 32-bit value. And if I go negative outside the range of the 32-bit result, then I take the negative number with the largest absolute value. So I saturate at either 2 to the 32 minus 1, or 2 to the 31 minus 1, or negative 2 to the minus 31. Or sorry, minus 2 to the 31, sorry. So these prevent wraparound that normally happens in 2's complement. We'll talk more about that in quantization lecture a little bit later. Our normal add does the usual 2's complement thing. It wraps around. So if I add, so for example, if I had a 2-bit number and I add, and my encoding would be for 2's complement, this is what? For 2's complement, this is what value? Signed. All right, what's this value? That's easy.
0.
0, good, we're there. Okay, and then for this one, it's signed. First bit is a sign.
So it's going to be 2?
1.
For 2's
2's complement. The first bit, 0, means it's positive, or sign negative.
Oh, okay.
Now 1, 1.
Negative 1.
Very good. See, to me, that's the hardest. That's the hardest one. All right, and then 1, 0 leaves you with
Negative 0.
negative 2. Remember, in 2's complement, you get that 1 extra. Yeah. So if in 2's complement, if I added 1 plus 1, I normally would get 2. And I'd either, so on wraparound gives me minus 2 would be the answer. Saturation gives me what? 1. Okay, so different ways I can handle this. Each has their merits. All right, and then to multiply 16-bit by 16-bit, I think it takes the low 16 bits out of the 32-bit registers. All right, so that's by functional unit, and of course there's a no op idle. There's those things. Now, if I group them by what they actually do, you'll see a lopsidedness. Lots of arithmetic operations, a pretty good number of logic operations, not so many bit management operations. And even worse, program control. I have one branch and it's unconditional. That should bother you, but some good news here. But data management, not a lot. I can load and store from a register to on-chip memory. I can move registers around. I can generate a constant. But not a lot of bit management, data management, or program control. Kind of weak on all three, actually. Great on arithmetic, pretty good on logic operations. So to build a truth table, not so easy. I can clear a bit, I can sign extend, it's a normalization, but there's no like branch of bit is set, branch of bit is clear, branch of bit is clear, and then set the bit. There's none of that. I have to spend 4 or 5 instructions to do any of those more complicated truth table type instructions. The good news is the DMA controller can do a lot of those things efficiently as the data comes in. So that's the good news. So the bit management is not very much in the CPU core. So we're going to rely on the DMA controller and possibly a coprocessor. and or a coprocessor, like an ARM processor on your OMAP chip. Let it do those more sophisticated truth table calculations. So I can do some basic truth table. I just take some extra cycles to do it. And then, oh, by the way, the S of multiply here is, for the multiply instruction, the S means signed, and for the add and subtract, it means saturating. Small detail. All right, so let's look at some code that we could write, or the compiler might generate. It's more likely our case. Or you might, in Lab 3, you'll look at some assembly code that other people have written. So here's a case where, and I'm comparing the C6000 against the traditional or more conventional digital signal processor from the late 80s. And the C5000 still lives on. This was a big part in 2G cell phones, but it has other uses. It's also in the early digital still cameras from TI and some other vendors, say about 10 years ago. Okay, so here's a C6000. And so we'll take a compact operation like add some constant to an implied register, or so this is going to, right. So I'm going to add some constant to a register, and the register is implied. Here I'm going to tell you, I'm going to first create a constant, and it's going to be F in hexadecimal or 15. So I'm going to generate the constant, put that in register A1, and then I'm going to add that constant to register A6 and put the answer back in A6. So all this is A6 equals A6 plus 15, so it's in hexadecimal, right, it's just F. And here's adding register to register, which is kind of what I did earlier anyway. I can't do direct addressing to a fixed memory location because generally in the DSPs we're doing we got lots of applications possibly running, and we like to go through an operating system to get a resource like a DMA controller. So we usually, the C6000 does not allow hard coding of addresses to local on-chip memory just because you don't know if you really have the right to do that. You have to go through an operating system to get a handle or some access to the driver before you can use it. So that's not even allowed in the C6000. Last one is indirect, which is pretty common in indexing into an array. So here so if we can parse this, I have a load word. So how many bytes am I going to read? That's long word.
32 bits.
32 bits, so it's 4 bytes. So I'm going to load a word, so this is 4 bytes. A long word is 5 bytes, oddly. Data unit 1 is going to do the work. My base address is A5. I'm going to offset A5 by 8 array elements, and each element's a word. So that means the total offset is 32 bytes. And then I'm going to post increment A5, the base address. And I'm going to take the result and put that into A1. So this is very much like C code would be. So you're saying I want A1 is going to be the contents of whatever A5 points to, indexed by 8, and then I'm going to post increment A5. Right, so if I had to write that in 2 lines, this all happens in the same cycle. Okay, but now to get the value into A1, I have to wait, 4 cycles of delay and 1 cycle of throughput. So this is very much like the C language. This is kind of the C idea of pointer arithmetic. Floating point extensions. Now this is where we're going to use floating point in the lab. So I have floating point. I need floating point addition, and the float data type is single precision. So float in C on the C6000, on the C6700 is 32 bits. This is the single precision, and double is 64 bits. Now, we don't need double precision. As I mentioned earlier, it's pretty rare, although I found out that the double precision or 64-bit float does get used in test and measurement equipment because they need more accuracy than your standard consumer electronics devices. So it does get used in that context of embedded system for test and measurement, as I found out last week. But normally we would not use double. Normally just, if we're going to use floating point, 32 bits is enough, because this already gives us 24 bits of mantissa plus sign and 8 bits of exponent. That's quite a bit. Now, so I have add single precision, and I need to multiply two single precision numbers together. So this multiply and add both have the same feature, which is interesting. They have 3 cycles of delay and 1 cycle of throughput. We'll need this in Lecture 5, Part 4, coming up a little bit later. Now, some other things we can do. This is reciprocal, which is 1 over x. It computes 1 over x for us, so we can use that for division if we want to. It's also used in graphics. Okay, so give you some members of this family and some price points just to be aware of in some application spaces. So again, your processor is right here. So this is the one used in lab. It's the last entry. And in particular, that's the one, right? That's the one in lab, is this 375. So this is the 6748 part in lab. So it tells you, this is again 8 basic operations per clock cycle. So 8 times this should give you 3,000. I've done my math right. On chip, this is in now kilobits, not bytes. And then there's a level 2 cache on some of these, but not all of these, as you can see. And here's your price point. So your processor, if you ordered 100 units, would cost you $20 a piece for what you're using. If you want to, but TIs sometimes will give samples out, like 1 for free. The boards are about $500 that you're using in lab. It's the OMAP L138 DSP experimenters kit. But you'll see what are some application spaces where you'll see audio being a big deal through all of this. And the reason, again, why is this so important? Well, for 32-bit float, you get 24 bits of mantissa plus sign, and 8 bits of exponent. And if you look at the data type that comes off of A to D converters for audio, the upper end of that's 24 bits. So if you pull in 24 bits of integer value from your analog to digital converter, you could exactly represent that in the mantissa, and the exponent would just be 0. And then you can do math with it, and then at the end, you can scale it and basically scale it 24 bits. Okay. There are a whole bunch of processors for the fixed point families. And again, you'll see a little more expensive, which is kind of weird. Normally, fixed is cheaper. There are some expensive points there. But largely, these are more expensive because they have higher clock speeds and more on-chip memory. If you were to compare the same clock speed and on-chip memory, the fixed point would be less expensive, which you can kind of see in this range. Now, these are older parts, so it's hard to, these are obsolete now. These are actually obsolete. Okay, so let me wrap up. I think that would do it. So there's some guides that you know about from lab for the different aspects of programming, debugging, and the board that we're using in lab. And that's it. Okay, thank you for coming, and we'll see you next time.
So that's a vacuum.
your labs because there wasn't any class on Friday. To like
Right.
reshuffle everything again.
Have to reshuffle again. It's okay.